Hi, I'm Zihan. I'm talking about our ICCV work, MonoFusion, Sparse-View for the reconstruction via monocular fusion. Before we talk about method, we need to understand our problem setup. Nowadays, there are tons of work doing 4D reconstruction from a single video. Although it's scalable, the problem setup itself is very ill-posed as it hallucinates a surface without correctly modeling the geometry. In training view, it might be okay-ish, but when changing the viewpoint, everything just collapses. There are also other types of work assume dense camera setup as they have access to full scene information. However, this setup is barely available in real-world application settings. Our idea is, can we meet halfway, use as few camera as possible to get true 4D scene representations, and we identify Eagle XO40 as a valuable source for this task, as it shows a four static cameras where each of them are 90 degrees apart, so there are basically no correspondence. So previous work on sparse view reconstruction failed to solve this problem as they are reconstructing easier scene and refer to sparse view cameras share dense correspondence. For this simple setup, if you just run code map, everything just works. But on our separated camera settings, those method fails to give reasonable reconstructions. So our motivation is sparse view reconstruction, where the cameras share little correspondence, is unintuitively challenging because neither dense view reconstruction or monocular reconstruction method are well suited for this kind of setup. That's where we propose MonoFusion. So the task is given input of Sparse-View 2D observations with field correspondence. The output we desire is a 4D metric scene representation that supports extreme novel view indices. So here presents a demo of a very realistic, highly occluded bike repairing scene. We start with those sparse view 2D observations, and we can actually get a 4D scene representation that enable us to do free view synthesis at any time and anywhere. And the secret sauce of how we're doing that can be summarized at three key points. The first is we need to get spatial temporal consistent depth. The way we do it is very simple. We create metric reference by running duster from the sparse views, and we simply align per frame monocular depth while applying transformation and background pixels. Moreover, static cameras means you can have free correspondence for free. That's why we further temporarily averages static background depth to alleviate the uncertainty predicted across different time steps. And the second part is we assume that semantic similar parts should actually move together. That's why we aggregate the Dino V2 feature from all cameras and just run a KNN to get them into different groups. Then we create some motion clusters with a shared SE3D basis. Finally, we run a joint optimization to optimize geometry, motion, and features together as regularization for our optimization process. Here we show some results on the normal time synthesis. We can actually do a very good job comparing to existing method. Further, we show a very small deviation normal view synthesis. Here we just rotate the camera by 5 degrees and we can show our method still performs very well. And finally, we show something very challenging to do a 45-degree normal view synthesis away from the training cameras. We can observe that MonoFusion compared to previous methods shows less noisy reconstruction with high fidelity foreground reconstruction and clean depth output. Here's the results on another dataset, Panoptic 3D, which we compare our MonoFusion output with the ground truth. We can barely tell the difference, and the depth output is very clean too. We further did analysis on the temporal spatial PCA feature. We can observe that the feature extracted by the Dino V2 is very consistent across different time steps and across different cameras.